Hey guys, this is Mrs. Mendy, and we talked about acceleration already. And if you haven't, then go back and watch that video. But now we're going to talk about calculation of acceleration. And there are two ways where we're going to calculate this. We're going to calculate this from the equation, which you're familiar with calculating from equations. So that's going to be very much the same as before. But then also from a velocity time graph. So that's a little bit different way of acceleration. And that will be kind of like how when we calculated velocity off of displacement graphs. So it's a similar kind of thing. Okay, so if you graph velocity versus time, and we haven't done that before, where you've got velocity on your y-axis and time on your x-axis, then the slope of the line is acceleration. Because remember, the equation for acceleration is change in velocity. Remember, delta means change in mathy speak. Over change in time. So change of velocity over change in time. That looks a lot like change in y over change in t, or rise over run. So the slope of that line of velocity versus time for any object, that's going to be its acceleration at that time. Okay, cool, right? That's what graphs are for, is to make math easy and accessible in a different way. Okay, so if here's an object, two different objects moving, and this graph shows their velocity over time. Okay, so the blue object, it has a constant acceleration. You can tell it's constant because remember, think right now, acceleration equals slope. Okay, if it's a velocity time graph, acceleration equals slope. So constant acceleration means constant slope. Constant slope means straight line. Okay, so like right here, this blue is constant. Right here, this red line is constant. And even though right here, this is constant, straight line, this is also constant. This is deceleration. I don't like when they say that. It's a negative acceleration. I should have changed that in this graph. Okay, so it's changing right here. So there's a change in velocity right here. So there's an acceleration between here and here. Okay, so, or a change in acceleration from there to there. Okay, so like any graph, you can calculate this slope, right? You can calculate this slope. So you can calculate acceleration off the graph. Okay. I'm gonna talk a little bit more about this and just show you how that is. So, like of the blue line, this blue object moving, what's its acceleration? What's its acceleration? Well, how would we know? Okay, well, it's changing from, it goes from acceleration, I'm sorry, a velocity of 0 to velocity of 10. So that's a change of 10. So it's 10 divided by how many seconds did that take? Because we're looking at change in velocity over time. So change in velocity is 10 over, don't do that, over 2 seconds. I can't gesture down there, you guys, but to see where it comes down to the 2, it comes down this line to the 2. So it's 10 divided by 2, or 5. Okay, the slope of the blue line is 5, so the acceleration is 5 meters per second squared. Okay, if you're looking here, the acceleration is 0. The slope is 0, so the acceleration is 0. For these two, the acceleration is positive because the slope is positive. Over here, the slope is negative, so the acceleration is negative. It's going from this fast to going slower and slower. Now, here's the weird thing that people get stuck on with things like this. Right here, where there's 0 acceleration, the object is still moving. It's still moving. It's not being still, okay, because it's got a constant velocity, but it's got a constant velocity of 8 meters per second, which is pretty fast, 8 meters per second. Okay, if you're moving 8 meters in 1 second, you're really booking. Okay, so constant velocity does not mean 0 velocity. Constant velocity means 0 acceleration, but not 0 velocity. Okay. Okay. All right, so you can figure out when something stops with negative acceleration, okay? So, and this is kind of funny because this is just using this equation in a way that is not immediately obvious. Okay, because I know you guys, I know you guys will be able to figure out just this. Like, if I give you like velocity 2 and velocity 1 and the time, you'll be able to figure this out. Okay, but I'm going to show you something a little bit more tricky. Okay, so if the acceleration is negative 2.2 meters per second, that means it's going slower and slower. It's slowing down. If this is negative, it means it's slowing down. How long does it take a car to stop if right now it's going 17 meters per second? Okay, so you're going to apply this acceleration, this negative acceleration. You're going to slam on the brakes. Okay, how long does it take a car to stop if it's going 17 meters per second? Okay, so what have we got from this equation? Okay, we've got, so I'm plugging in some stuff. Okay, we've got acceleration equals negative 2.2. So for acceleration, I'm plugging in negative 2.2. Then we're going from, we know that we started with, V1 started with 17 meters per second. So for V1, I'm plugging in 17. Okay, now 0. Here's the 0 for V2. How do we know that? Well, we know because we want it to stop. Okay, how long does it take it to stop? And stop, by definition, means zero velocity, no longer moving. Okay, that's what it's stopping. Okay, so if something comes to a stop, it's v equals 0, velocity equals 0. If it goes from being still, from stopping, and then starts up, anytime that you're stopped, the velocity is 0. Okay, so you can plug that in. All right, so now from this, you just do your algebra thing on it. Okay, because here's your equation. To me, the real work is done. Now all you do is some math plug and chug. Okay, which I realize is not always, the easiest thing for everybody, but it's a different thing. Okay, if you can't get it from this point, that's a math thing to practice rather than a science thing to practice. Okay, but we're going to do the math. Okay, so I multiply both sides by t. So I get negative 2.2t equals negative 17. And then you divide both sides by negative 2.2. So you get t equals negative 17 divided by negative 2.2. And you get 7.27 blah, blah, blah. Okay, oh, I should have put seconds on there. Oh, bad teacher. Didn't put the unit. Okay, so how long does it take a car to stop? 7 and about a third seconds to stop. Okay, so you can do that. You can figure out when something's going to stop. Oh, I did. Ha ha ha. Okay, good. All right, here's another special case, is acceleration of a dropped ball. So there's a ball up in the air, you're up on top of a building and you just drop this ball. Okay, now the acceleration from gravity has a special name and we call it G, because G for gravity, gravity on the earth, which almost everybody is all the time. So that's okay. There are different accelerations from gravity depending on where you are in space and what planet you're on. But we're so much on Earth that it just has a special name. It's G. And it's 9.8 meters per second squared. That means if you drop anything from a height, even you jumping up in the air and falling from like the 2 feet up that you jumped, you're going to fall at with an acceleration of 9.8 meters per second squared. That means you're going to get 9.8 meters per second faster every second that you're dropping. I'm going to say that again. If you drop something, it gets faster. It goes from still when you drop it to getting faster and faster. It gets 9.8 meters per second faster every second. That's what this means. 9.8 meters per second squared means 9.8 meters per second every second faster. Okay, so you can figure out how fast this ball is going at any time after you drop it. Okay, how fast is it going after 3 seconds? Well, let's figure that out. Okay, here's our trusty equation for figuring out acceleration, but we've got 4 variables in here. 1, 2, 3, 4. And we know what all of these are except one. So except one. So how fast it's going at any time, that's going to be v2. Okay, and we're going to set what v2 we mean by saying that this is 3 seconds. So the time is 3 seconds. We know what the acceleration is, right? Because the acceleration from gravity on Earth is g. It's 9.8 meters per second. So let's plug that stuff in. Okay, so acceleration here is from this g. That's the acceleration because we're dropping due to gravity. And that, why did I put, oh, because 9.81 is a little more precise. Sorry, guys. Okay. This is how I won't, you just need to know it to this. This goes out further than this because, with real science, you get messy numbers because that's just how the universe is. Sorry. Okay, V2 we don't know because how fast it's going after 3 seconds, that's what this is. This is how fast it's going at 3 seconds. V1 is 0 because it wasn't moving at first. We dropped it, and before we dropped it, it wasn't moving at all, right? And then the time is 3 seconds. So from here, now everything is set up. Now it's just plug and chug. Okay, now it's a math problem. From going from here to here, that's a science problem. But from now on, it's a math problem. And here we go. Okay, so we multiply both sides by 3 to get rid of this 3. The 0 goes away. So it's 3.981 equals this. We multiply those together, and we get 29.43 meters per second is how fast it's going. And okay, for reals, this is in a vacuum because you're pushing aside air all the time, that there's gravity on Earth down where we live, but this calculation ignores that. Okay, which is fine. It's fine. When you're starting out in physics, you just ignore all kinds of stuff because it's too complicated. We're just trying to get you to get the basics of it. Okay? Okay. Okay. Now, okay, acceleration of a ball thrown straight up. That is sort of the same question, but in reverse. Okay, so this is another special case. Um, but let's just go through this and I'll show you what I mean. What happens when you throw a ball up in the air? Okay, the acceleration from gravity is still there, but now it's slowing the ball down because it's pulling in the other direction. Okay, it's kind of weird. Okay, if the ball has upward velocity of 5.7 meters per second at first, V1, when you throw it up there, when does it stop moving upward? Okay, that's kind of weird, but you know how this happens, right? You throw a ball up and it goes slower and slower and slower until it gets to that point where it's not moving at all. And then it starts falling back downwards. Okay, so you know from that the ball is going the fastest it's ever going to go right when it leaves your hands. Okay, which is kind of funny to think about, but right when it leaves your hands, that's the fastest it's going to go. And then it goes up, up, and gets slower, 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 and then it falls back down. Okay, so let's figure out, when does it stop moving upward? Okay, here's our equation. Everything we need to know is here. We've just got to plug the stuff in. Okay, so upward velocity v1, we know that this is here. We know that the acceleration is from gravity, but remember, acceleration is a vector. It has a direction, just like velocity. Okay, so let's plug some stuff in. So now this 9.8 is negative because it's going in the other direction. It's going against our velocity. It's taking away from the velocity. So we're going to have this velocity, but every second that it's traveling, gravity is slowing it down. So this is negative. It's slowing it down. Okay? And then it started. So V1 is this, and we want to know when it stops moving. When it stops moving, that means stops moving is 0. So that means the V2 is going to be 0 because it stopped moving. Okay, so this is, we want to know when it stopped moving. This is how fast it was going to begin with. This is how much slower it's getting every second. Okay, And you can think about whether the velocity is positive or negative, depending on whether it's your velocity is adding, or the acceleration is adding to the velocity, or is it taking away from the velocity? Okay, so if you're on top of a building and you threw the ball down toward the ground, then gravity would be speeding it up. So then that would be positive. But since you're throwing this against gravity, you're throwing the ball up against gravity, then it's going to slow it down. So then this is negative. Okay, and we're going to try and solve for t. All right, so once all this is plugged in, the science work is done, the math work begins. Okay, so we've got to multiply both sides by t to get t by itself. Okay, and then after we got t on both sides, and it canceled out over here, I didn't show that part. Then you're going to divide both sides by 9.81. Okay, so it's 5.7, so it cancels out on this side, so you have t by itself, and then 5.7 divided by 9.81, and then it's some calculator work, and you get t equals 0.58 and some change, and that's how many seconds it takes to stop. Okay? Okay. I know that one's a little bit weird, but people have really cared about throwing projectiles, and a lot of this work was done to think about throwing projectiles because humans are a violent people, and we were always like throwing stuff at enemies and like knocking down their castles and stuff. For real. That's where a lot of shooting cannons and stuff, and people wanted to know how this was going to work. Okay. Shoo! That was enough, right? Okay, calculation. All right, that's it for now.